Thank you, everyone, for coming back. I know yesterday at the end of my talk, I was kind of promising a bunch of things today, but to paraphrase the military strategist Helmut von Moltke, no lecture plan survives first contact with the audience. So am I okay? All right. So let me just remind you, I think I want to just fill in and try to clarify some of this picture I'm trying to bring together. So I'm trying to connect something in homotopy theory with something from the world of some kind of gapped Hamiltonian lattice models. And I'm being a little vague about exactly what those are because I don't totally understand the definition. But let me just say phases of Hamiltonian systems. So lattice systems or something. So over on this side, there's a conjecture of Alexei Kitaev that connects these, and I'm just exploring this relationship in these talks, trying to kind of look at things on both sides and see how they might line up and what possible avenues we have to prove these conjectures. So on this side, there's this thing I've been calling K, which is actually a spectrum. So maybe that even belongs over here. So this will be, I'll call this Kitaev spectrum. And it's supposed to be defined on this side. So something wrong?
K stands for Kitaev.
Oh, yeah. Well, I'm good. I snuck that in. Yeah. So, yes. Okay. So when I write down a spectrum, it consists of a sequence of spaces. And so all right, let me just, so that means, so the Kitaev spectra, that means there's a homology theory. So there's the Kn cohomology of a space, and there's the Kn homology of a space for every n in the integers. And this Kn of x is formally, it's homotopy classes of maps from X into a space, which I usually, whatever the symbol is, I usually like to write that as an underline with an upper N. That's the object that represents this functor. And Kn is supposed to be the thing I called K of Rn, but this is supposed to be phases or Hamilton, some sort of lattice models on Rn. It's somehow made into some sort of, it's made out of some object that belongs to this world. And Alexei produced some arguments showing these form the spaces in a spectrum, and he made a conjecture about what that spectrum is. All right. Invertible, yeah, I said some kind, I mean, there's all kinds of adjectives that go here. So invertible, but yeah, that was an important one to put in. Invertible, gapped, topological, there's a number of adjectives that have to go in on this side. And all right, and so that gives you a spectrum in the sense of algebraic topology. And then there's a conjecture about what this is. And in the language of spectra, K, the Kitaev spectrum, is supposed to be equivalent to, in this flavor, it's supposed to be equivalent to something we call, that has a, it's one of these things that's built out of more primitive pieces. And so the name in topology is a combination of a lot of symbols. All right. This is some kind of Anderson dual functor. This is some sort of duality functor that replaces things by their character groups. This is spin boardism, and this is a shift of indices that makes things line up. So I wish I should probably introduce a better name for this. This always happens. You combine a bunch of objects in a new way, and your first notation for them is some very compound symbol that's a little bit hard to describe. Okay, so in my first talk, I described why there's a map just to this, and then the question is, why is there a map if I put this here and yeah, okay, sorry, I'm just trying to make sure I follow my notes. Okay, right. So I want to make a diagram. And so in my first talk, and Alexei, and I think in his talk mentioned, there's a map from here to here. And so the thing about this spectrum, about what this is it's easy to map into. And there's kind of a universal property that lets you map into it. And in this case, it comes from the property that K0, K1, K0 is the circle, which is something you can calculate, or C, I was writing it as C star, and that gives you a map into here. I'm still a little worried about it having index off, but I'll fix that later. Okay, so this map is easy to construct by a universal property, and then the interesting thing is, why does it lift all the way up to this? So this is supposed to have, there's supposed to be this map here, and that map in terms of physical systems, this is supposed to be a consequence of reflection positivity and an emergent, I'm just going to say Lorentz symmetry, but I might be, that might not quite be the right word, but there's some emergent spin, there's an emergent symmetry that gives you spin invariance. Okay, so how can we approach this? Well, one way to do this, let me find my diagram here, is to find something down here. Okay, so down here, the homotopy groups of this we know. Let me find my diagram, I'm sorry. So I wanna, okay, yeah. What I wanna do is find something down here, okay? So something down here will correspond to some kind of topological quantum field theory for framed manifolds. And I want to find something down here that does not lift here. And then I want to ask myself, can I construct a lattice model for it? So the idea is I'm going to find something down here. I'll explain in just a second. I'll call it kappa. And we'll find some kappa here, which is actually a certain five-dimensional TQFT for framed invertible TQFT for framed manifolds, okay? And I want to say that there does not exist a 5D TQFT here. Okay. There does not exist a five-dimensional here. So then I want to take the problem of finding a lattice model for it. Okay, so here's the flow chart. Okay, so I haven't told you what this is. I'm going to say in just a minute what it is, but I'm going to write down a certain 5-dimensional TQFT here that I know for sure does not lift here. And then I want to know, can I find a lattice model? Or I'm sorry, this is a 5 plus 1D. Topological quantum field theory. And I want to know, can I find a 5-dimensional Hamiltonian lattice model for this theory? Okay, so here's the flow chart. Try to find a lattice model for kappa. Okay, so there's two possibilities. One answer is, oh, sorry, that's not how you make a flow chart. Try to find, oh yeah, all right, oh yeah, that's how you do it. So can you do this? So the answer is yes, or can you? Okay, that's what, okay, so the answer, if the answer is yes, then the conjecture is false. If the answer is no, well, then what you have to do is ask somebody smarter than you. And then, so that returns you to here. And then, since there's only finitely many people on the planet, this process terminates. At the end, we would know that either it's not possible to do this, in which case the conjecture is probably right, or we find an obstruction. All right, well, so that was a kind of mirthful way of explaining the strategy. But what I really want to do is what I want to say about this is that the general process of trying to find lattice models for known phases is going to inform us about the possible restrictions that Hamiltonian lattice models put on general topological quantum field theory. So the idea is that not every TQFT should come from a lattice model, and we want to introduce. I just wanted to investigate this question. If I take some known TQFTs, what prevents me from finding a lattice model for them? And then we can hope that whatever obstruction we're running into or whatever tools we need to recruit are that those might tell us the origins of where this emergent Lorentz symmetry is, or they might tell us the role that reflection positivity takes. So in my last two lectures, today I just want to frame this question a little better, and then in tomorrow's lecture, I'll try to give you some very concrete examples of how you go from what it takes to go from a topological quantum field theory to a lattice model. So just to be concrete, and just because I promised you I would do it, I would let me just look at what's happening in dimension 5, okay, or dimension 6. So I think I'm supposed to be looking at, I want to look at sigma 2 IZ. Oh, sorry, I want to look at K underline 5. So it's a 5-dimensional lattice system. So down here I have in this crazy notation sigma 2 IZ underline 5, and I want to calculate pi 0 of this. So if you go through, this turns out to be the character group of pi 6 stable of the sphere. And pi 6, here, I'll just write down the first 6 homotopy groups so we know that have them up the board. So pi 0 is the integers Z2, Z2, Z mod 24, 0, 0, Z mod 6, and then it goes on. And here's the group I'm interested in. And everything here, more or less, lifts up to the spin case. Okay, more or less everything comes from the spin case, but this one sort of defiantly does not, or that's a Z mod 2, I'm sorry. And that Z mod 2 in topology, that's generated by a class called nu squared. If I think of stable homotopy as framed cobordism, that's SU2 cross SU2, and it's left invariant framing. We're interested in a character of that, so we're interested in an invariant of these. And in this particular case, that invariant comes up. I mean, it's of course ancient in algebraic topology, but it comes up in physics in Witten's paper on the 5-brane effective action in M theory, where he shows how, given a 6-manifold with certain structures, you can write down a quadratic function on the middle cohomology, and then the ARF invariant of that quadratic function defines the character. I only mention that because there's sort of connections with this in M theory, and so connections with physics, and that might lead to better ideas than I have about whether you can or cannot make a lattice model approximation to this, something in dimension 5, that a 5-dimensional lattice model. All right, and just to complete the
Yeah, we'll talk about this Z2 part. Is this what is topological invariance can be written in the Stiefel-Whitney class? Like this
No,
function.
you
So
can't
it's
write it.
beyond that.
Yeah, it's beyond Stiefel-Whitney classes. You can't write it. So another way you get invariants are like take an index of some operator. It's beyond that. That's why everything up until here can be described as something along those lines. Is that, yeah, so that's what makes this one really, really different. Yeah, Ezra.
Maybe it's relevant, but was that 6-manifold oriented or spin?
So that 6-manifold is more than that. So that 6-manifold has it has an integer lift of W4. Okay, so spin manifold automatically has that, and that class is divided by 2. Okay, so that's what gives you the invariant. So a string structure would give you that, but the minimum thing is, yeah, dividing that by 2. Okay. Okay, so, and if I was up here, actually, maybe just in the interest of time, this group, so that group is 0. So I think just in the interest of time, I won't expand on that, but to get back to your question from yesterday, right? I was saying all the characters here come from Stiefel-Whitney invariants or index invariants, and this is the first place where you can't detect anything like that. And yeah, this is also not a very difficult
Maybe
calculation.
another related question. You know, like we have fermions, you require manifold to have spin structure.
Yeah.
For invariant to be well defined. For this kind of invariance, what kind of manifold?
Yeah.
All kind of manifold, this invariance can be defined, whether there's some complete calculation.
Yeah, I mean, so spin structure is the vanishing of, in topology, is the vanishing of W1 and W2, and this is the vanishing of W4.
So that's a necessary condition.
Yeah, that gives you the invariant. I mean, that once you have that, then that invariant is defined.
W4.
Yeah, but what that means, so yeah, I was explaining it in a different way to Ezra, but yeah.
But I'm just thinking in terms of Gayotto-Kapustin now, that there's some explicit chain, Z2 chain.
Yeah,
triangulation, which is this structure.
Yeah, so I think one of the things that makes it challenging is how to geometrically invoke this structure, but all right, anyway, but there is a theory there, and it's hard to say a lot about it, I think, okay. But the general question is, how do I start with some abstract topological quantum field theory and go back and produce a lattice model, and what kind of structures am I looking for do I need to do that? And are those the structures that are relevant to having an emergent Lorentzian symmetry?
Here, let me confirm. So W4 equal to 0 is a if and only if condition for this invariant to be defined. That's strong.
Yeah, I think
Okay.
that's, yeah, in that dimension, yeah. Well, W1, W2, and W4.
They all, so W1, W2, W4, they all equal to 0.
Yeah,
So
yeah.
if-
But it's even, I mean, you really need coaching, you need, not, you need more than just witnessing that they're 0. You need, like a spin structure witnesses that W2 is 0, but it's more, it's a way of making W2 0. It's the same. So strings is, yeah, so that's that. All right. Okay, so I need to go, I want to talk more about these objects, and to do that, I need to bring in the cobordism hypothesis. This was formulated by Baez and Dolan, and then reformulated and proved by Jacob Lurie in a kind of in an amazing vision, really. Okay, so there's a lot of stuff to unpack, and I'm going to try to just be as brief as I can. Oh wait, oh shoot, hold on. Sorry, I got ahead of myself. Sorry, I got ahead of myself. I wanted to say something else about, I wanted to sew up another loose end about yesterday, from yesterday, and try to and connect and just also try to just unpack a little bit more about what this thinking is. So here's a question that came up yesterday, and I kind of stumbled on my feet. So we know that the M-spin homology of a space is this cobordism group of maps from closed-end manifolds to X. And then the question that came up is, what's the M-spin cohomology of X? And there was there's a model Quillen gave when X is a smooth manifold, and there's another model that's probably due to Frank Quinn when X is a space. And that's what I sort of meant to, I wanted to say something about that. So let me just say what it means to give an object, something in M spin 0 of X, and then we'll try to think about what it would mean to give. Yeah, okay. So let me first try that. Okay, so what do you do here? You imagine that X has been triangulated. So let's suppose X looks like this or something. And then what you have to give is, for every vertex of X, you give a 0 manifold. If I'd written n here, I'd give a manifold of dimension -n, and there'd be a picture that, I'll say something about that in a second. So I'll just draw that sitting over this. So sitting over this, I've got a 0 manifold over every vertex. Maybe it's empty up here. And over the intervals, I have a cobordism between them. And so there's there's a cobordism. So let me not draw all of those. All right, so over the intervals, there's a cobordism, and and over the faces, there's a cobordism between the cobordisms. So maybe these are just the identity cobordisms down here, and then I have to draw this picture very well. I'm supposed to draw a cobordism between the cobordisms. I screwed something up. Anyway, it's supposed to be a cobordism between the cobordisms and higher. And if I had had n equals -1 here, or n equals -2 here, then this would have had to have been empty. This would have had to have been empty, and I would have wound up with a zero manifold over the interior of this face, etc. So you're supposed to think of it, that's what I meant by, you're supposed to think of these as families of manifolds moving through cobordism parameterized by X. So the vertices give me families of give me zero manifolds, the edges give me one manifolds that are cobordisms, and and everything else. Okay. Now, why is this is the one that's relevant to what I want to talk about, because what is I sigma 2 IZ for the M spin I want to smash that with X and take the zero space. Okay, so that's the analog, that's the space whose homotopy groups would be this homology of X. Now this is, or I want to compute, let's say I want to compute pi 0 of this, its path components. So this is just, don't be kind of dismayed by these symbols. The manipulations will work just fine if you think of these as vector spaces. So if that's a vector space and this is maps of this space into this is tensor and that's a vector space. So that's maps, say, from the trivial vector space into this. All right, now if X is a finite dimensional vector space, or a dual or a finite cell complex, it'll have a dual. So that's the same as maps from the dual of X into this crazy combination of symbols. And that's the same as maps from this tensor, the dual of X, into this. And that's the same as maps from M. That's the same as maps from the space of maps from M spin into X into sigma 2 IZ. And that's essentially, you know, if this was C star, that's essentially characters of M spin 0 of X, of M spin upper 0 of X. And that's what I just got done describing over here. So the thing that would have been, that's relevant to us on this side is characters of that. And character should be, a character of a Bordism group should be regarded as a proxy for topological field theory. So it's kind of a topological quantum field theory defined on kind of diagrams of manifolds that sit over X and move through Bordism. So this is some elaborate structure on kinds of manifolds, and this is some kind of topological field theory like that. And on the other side, on the Kitaev side, so we could look at the Kitaev homology. So if you go through the definitions, if you go, you know, this is the direct implication of the definitions. So that's the thing I was writing as K of X. And in terms of the Kitaev spectrum, its path components is pi 0 of the zero space of K smash X. But whatever, it's just the it's that, and in Kataya, so I described this picture a little bit yesterday, but you think of the what it is, it's some sort of a lattice model on everything you see. So inside every n simplex, I have some Hamiltonian lattice model. Here I have a boundary condition for it. That's maybe a boundary to the vacuum. Here I have a lattice model on the line, and here this is some sort of boundary system, et cetera. So it's lattice models. If X is a smooth manifold, then this will just be a bunch of phases and domain walls and defects between them. And if it's more complicated, it'll just be, I mean, this will be like a lattice model here regarded as a domain wall from the vacuum to itself and on down. And so this expression isn't, these are supposed to sort of look the same to you, that if we think of lattice models themselves as approximating topological quantum field theory, just expanding this out in the language of spectra, this is just the natural outcome of regarding this as a spectrum and regarding Alexei's picture, his theorem about that being an infinite loop space and his conjecture. So this is a picture that I'm going to expand upon, but I just wanted to indicate that just the standard maneuvers in homology and cohomology, they are all expressible in this lattice model side, where you think of this is some type of material, and the sort of instructions for build, like I'm trying to build X out of this, out of a sequence of material types, and that's what this side gives me. Okay. Oh gosh, I'm going slower today. Okay. So let me quickly. So now I want to get back to the cobordism hypothesis. Oh, was there a question?
Yeah, sorry. So when you have this picture of material, you're assuming that it's somehow homotopy invariant.
Could you speak up?
The question is whether I'm assuming this type of material is homotopy invariant.
Yeah, because X is essentially just like a homotopy type.
Yeah. I mean, I think this is. The fact. I mean, I think I'm just going to have to say it will work out that way, but yeah, let me not get bogged down in that. I think this is just, yeah, let me try to talk about that a little bit later. Yeah.
That each type of this picture corresponds to
no. So the interior of an n simplex, that corresponds to an element. Oh yeah, each type like this corresponds to an element of pi 0 of kx.
So, I forgot if you defined it, the homology in this the last lecture, but is it correct that given a space X, this X is consisting a space consisting of so collection of lattice models and domain walls connected in a way that to make the simplex according to the simplex triangulation of X.
Yeah, it's like
And,
that.
So in that case, I maybe stupid question, but I got confused about the factoriality of this construction. Do you have
Yeah, I'm just, I don't think I can fully answer that now, and I'm getting anxious about running out of time. So I'll just say one thing is I could map X to a point, okay, and then the pi 0 k of a point is just this line bundles. lines, and then that map sends a particular model to the ground state. So that's how that's supposed to work.
Actually, trivial operation.
Let's pick, it's more elaborate than that. I just wanted you to have, I wanted to have a picture up about how the Kitaev homology is supposed to work, because I want to, well, let me make my point. So the cobordism hypothesis it's this amazing fact. So I'm going to write, all right, so I'm going to start with a map of a space B to BON, and I have there's an N, a number N chosen, and I'm going to look at board N of B, although this symbol, the N appears twice because in this map, really this should just be called like board zeta or something, but I'll leave all these symbols in. So the objects, so this is an infinity, this is a symmetric monoidal infinity N category with duals, and I'll say something about that, but having duals is a property of a symmetric monoidal category. So the objects are zero manifolds. M mapping to B plus an isomorphism of the tangent bundle of M plus Rn with the pullback of the bundle classified by zeta. And a morphism is a cobordism. So the one morphisms are cobordisms. And in general, the K morphisms are cobordisms between cobordisms, etc. So these are certain kinds of K manifolds. M with corners and equipped with a map from M to B and an isomorphism of the tangent bundle of M plus R n minus K with the pullback of zeta. Okay, now that's not all of the morphisms. There's more morphisms, and those are diffeomorphisms. So the N category means I have morphisms up to degree N that I've described, and those are not necessarily invertible. But the infinity means that I have higher morphisms all the way up to infinity, but everything above N is invertible. So I have diffeomorphisms and composites of diffeomorphisms, paths between diffeomorphisms. I have the whole diffeomorphism group of a manifold. So if I have a closed n-dimensional manifold, that's an n-morphism from the empty n-1 manifold to itself. And so that's just an n-morphism, but then I have the entire diffeomorphism group of it. So all the homotopy groups of the diffeomorphism group of that manifold appear as even higher morphisms. All right, and now, so this category, this has duals. I'll just, I'm sorry, just in the interest of time, I think I'm not going to write this down. I mean, this, maybe everybody already knows this, but if I take if I have every manifold, I can take the same manifold with the opposite orientation and cross it with an interval and get a map from this manifold. Oh, the symmetric monoidal structure is disjunct union. And then I get a map from that manifold, tensor another one to the empty, to the unit, and this that makes this into a dual of this. But it has duals all the way up. Every K morphism has a dual or an adjoint, and there's duals between the duals. And so, so what we say is that the objects here are fully dualizable. Everything that participates in representing something as the dual of another itself has a dual. And we also, another way we say this is that this is a category, this is a symmetric monoidal infinity n category with duals. All right, so but being with duals is just a property. And so the cobordism hypothesis says, so this is a theorem worry that board n point is the free infinity n category with duals on one object. And there's a nice description. So that means that a functor, a symmetric monoid, the free, thank you, yeah. An infinity n category with duals on one object, which is a point. And now notice, what is that point? That point, that's a point plus an isomorphism of the tangent bundle of a point plus Rn with Rn. So this is an element in On. So there's really, there's an On action on that point. And there's an ON's worth of points. Okay, but it's the free thing on just one of them, and then there's this ON action. So in particular, so a topological quantum field theory is a functor, is a symmetric monoidal functor to some other symmetric monoidal infinity n category. And suppose it has duals. And these Z's are just in one-to-one correspondence with wherever Z of any given point goes. Okay, now, if I want to understand all functors, I should think about natural transformations between them. But a natural transformation between symmetric monoidal functors like this is automatically a natural isomorphism. And so the aggregate of all functors, write this for tensor functors, so that's just that is just the objects in C, but I only allow, the only natural transformations between these are isomorphisms. So I'll write it like this. So C tilde, so C tilde is the maximal, the largest infinity groupoid. In C, meaning the largest subcategory containing all the objects and all the invertible morphisms and two morphisms, etc. Okay. Okay, because it's because a map, let's just think about it with vector space. Okay, so suppose I have a functor from vector spaces to vector spaces that that's symmetric monoidal, and I want to look at a natural transformation between those. Okay, so so that'll send V to some T of V, and it'll also have to send the dual of V to some dual of T of V, because the being duals is something you can measure. It's just a consequence of being symmetric monoidal. All right, so now if I have that means if I have a map from V to W, I get a map from if I have a map from V1 to V2, I get a map from T of V1 to T of V2. And then, now I'm getting myself mixed up.
I think that's.
Oh, I have two functors and a natural transformation. Sorry, I'm just gonna say it in words. I'm really sorry. If you have a natural transformation, it sends, you get a natural transformation from T1 of V to T2 of V, but you also get a natural map from T1 of V star to T2 of V star. And that's the same as T1 of V dual, and that's T2 of V dual. And so this map gives you a map from this in the other direction, and those turn out to be forced to be isomorphisms. Okay. Well, there's a whole infinity category of functors between them, but the only transformations happen to be invertible. So it is so I'm thinking of, identifying infinity categories in which all the morphisms are invertible with spaces, and so that's a mapping space. Okay. Framed. I'm sorry. I got point. Yeah. So I'm just taking a point up here. So that means, remember, I had this X, I had this B over BON, and I had my manifold, whatever it is, tangent bundle plus Rn minus K, and a lift here. And now I'm taking this B to be a point. And so, I mean, it's framed.
So confusing because you said this theorem is that this category is free, which means that there is only one such functor, right?
It means that it's free on one object. So a functor is determined by what it does on one object. So the set of all functors is the set of objects of this. And then the only natural transformations are equivalences. And so the space, or the category of all functors, is just the space of all the objects and the isomorphisms between them. Is that okay? Okay, so, all right. Okay, so I want to say one other thing. What happens with this B over BON? Well, ON, so there's an amazing corollary of this, because ON acts on the set of objects of this category. And so this point has an ON action. And so every dualizable object, every object in an infinity n category, in any infinity n category with duals, has an ON action. Another amazing thing is that if I look at just the closed manifolds of dimension n, then what's inside this category is the classifying space of the diffeomorphism group of that manifold. And according to the hypothesis says is that the diffeomorphism group, the B diff of every manifold, is accounted for merely by the rules that give me higher and higher order, higher duals between objects. So this notion of being in duality is essentially combinatorial in nature, and so is the notion of being fully dualizable. But that aggregate of combinatorial conditions contains in it the classifying space of the diffeomorphism group of every manifold. So it's a really, really striking theorem. But anyway, what I wanted to say was ON acts on this C tilde, and what I so the other theorem is that the tensor functors from board N B into C, that those are the same as the space of sections that space is equivalent to this space of sections here. So it's a description of this board NX for any, or board NB for any B, in terms of duality in this ONX. Okay, so now I got to go back to something. Yeah,
Where the fully realizable objects, right?
no, I assumed every object was fully dualizable. C twiddle is the maximal groupoid. Everything's an isomorphism. Okay, sorry. Okay. Right. So
Something.
ON is the change of framing on the one manifold. Yeah.
Over somehow. The fact that.
Because it's a functor, right? This point has an ON action on it, and so because it's a function. So, right. All right, I've got to wrap this up. I had a complicated point to make and an easier point to make. So let me try. I'm going to try to do both of them in 5 minutes, but I'll stop on time. So we have. All right, so I want to. Oh, shoot. All right, let me try to abbreviate something here. So we had this diagram, we had this we had this space, this sigma to IZ to the M spin. So that was some spectrum, and we had a space for every N for those. And those are some kind of n-dimensional topological, invertible topological quantum field theories. All right, but by the cobordism hypothesis, at least n-dimensional, or these are like supposed to be n+1 dimensional TQFTs with some sort of spin invariance. Okay, so that by the cobordism hypothesis, that's supposed to correspond to a functor from board N point to some category, and we've decided, I mentioned last time, there's these universal target categories, which I like to write like this, and that's so that's n+1, like that. Okay. And I won't spell this out, but these are supposed to happen to be invertible field theories, and it's sort of part of this package of the cobordism hypothesis that when they're invertible, this becomes an object in stable homotopy that looks something like this. All right, so this is just determined, this thing just corresponds to some object, let me just say X, or T for material type in Cn+1. So this Cn+1, this universal thing, is some sort of moduli space or moduli category of n-dimensional sort of electronic material types that out of which we build topological field theories. Now, there's two things that cause a mismatch between this picture and this one. So, and I think they're both of these things are important to this problem of starting with an abstract topological quantum field theory and making a lattice model. So there's two I don't know how to spell janky, two rattling problems. I know, I'm no longer, ever since spell checkers, I've lost my ability to spell all words. So I'm just going to say two problems, two mismatches here. Okay. So one is, so A, there are a lot more maps in this Cn+1 tilde that beyond isomorphisms. And we really need those maps. We can't just throw those away. Those maps appear when I want to say that one object is a dual of another. The map from W tensor W dual to the ground, to the tensor unit, is not an isomorphism. And so if I'm picking out objects here to be these theories, I need to be thinking about these other maps as participating in the discussion. And I'm probably losing something by passing purely to homotopy theory and ignoring them. So I want to say something about that. And the other point is that down here, I could form board n+1 b spin n plus 1. I have a spin n+1 action here, but not. Okay, so that means that corresponds to an object T in Cn+1 that's equipped with fixed point data. For spin n+1, so that's what it means to have this lift, and all that means that this is equipped with fixed point data for spin n+1, but I don't have spin n+1 up here, I have spin n. Okay, so you need spin n. All right, so I think to kind of really connect this sort of homotopy world with the sort of lattice model world, before we really get started, we have to come to grips with these two pictures. And I don't even know how to combine these correctly in this purely topological quantum field theory, but they correspond to questions in lattice models, and I'll try to say something about those. So in part A, even though I may be only interested in invertible theories, I probably need to avail myself of other morphisms in here. And these other morphisms, so the other maps, are domain walls and higher order defects. So we'll see tomorrow. Oh, I'm going to have to go just a little bit longer. So we'll see tomorrow that writing down a lattice model, sort of, you wind up needing to avail yourself of domain walls and defects and higher order defects. And that was what I was saying. I sort of want to, so one idea is I want to extend, or this, I was suggesting this yesterday, is that modify the definition of this space Kn or K of Rn or something, right? To include domain walls, defects, etc. These are already part of the language of Hamiltonian lattice models. We know what a boundary condition for one is, and there's presumably defects and higher order defects and everything. But I want to propose that the analysis, even in the invertible case, the analysis of this space where these are maybe systems of RG flows of lattice models, or IR limits or something, that this be modified to include domain walls and defects and all that. And then we would interpret the domain walls as one morphisms, the defects as two morphisms, et cetera. And I think it would be a nice picture if these spaces kind of were organized to include all these, or in other words, if these moduli spaces of Hamiltonian lattice models could be organized into an infinity n category, where the objects are the models on Rn, a domain wall might be a model on, or a boundary condition would be a model on a half plane that I'm scaling out of, or maybe I have a domain wall between two, but just to model all the natural apparatus that we actually know is there in the world of field theories. I mean, that would include in it, if you could do that, it would include in it as a consequence that the invertible ones formed an infinite loop space. All right, now the other part, and then I'm sorry, I've gone a little bit over. The other part has to do with the spin in and not spin. So Dan Fried and I showed, so there's a theorem. So this is a paper from a few years back with Dan Fried called Reflection Positivity. And invertible topological phases, but probably if you just search Fried, Hopkins, REF, it'll uniquely complete to that paper if you're looking for it. So in that paper, we do two things. So we gave a definition of reflection positivity. For invertible topological field theories. Okay, so I just want to think of that as an object in here that's a fixed point for spin n+1, or we had a whole list of groups. This could be more or less anything for our definition of being reflection positive. And then we showed that reflection positive on the invertible phases implies that T is a spin n+1 fixed point. T is actually implies it's a spin. So that gets you up to here. Now this is a sneaky thing. So if it's invertible, the spin n+1 action automatically extends to a spin action, but it isn't necessarily being a fixed point here does not make it a fixed point for that. And that was a key part of our theorems really couldn't go beyond the invertible case. And so that's meant, oh, I've erased it, but that's meant to get rid of, so that this other point about, I had these two, yes. This point here, that this is somehow this point here, B, is somehow supposed to have to do with reflection positivity. Now, I don't know all of the progress that's been made, but there's a big group of people. There's like 1, 2, 3, 4, 5, 6. Well, there's a lot of people involved in this project on, so I think they call the Dagger Gang. Or the Dagger Group or the Dagger people or whatever, but it's, I'm sorry, there's Giovanni Ferrer, my own writing, Cameron Krulewski. Lucas Mueller, Luke Mueller. Uh-oh. I'm gonna write really sloppy because that's what I did before. Pennies. David Reuter. Claudia Scheinbauer. Luke Stein. All right, sorry, my spelling, I've lost that. Uh-oh, where's Theo? Theo's on there. There's a big group here, sorry. Everybody, yeah, I'm sorry. I wrote I wanted to get there's a big group that's working on higher Dagger categories, and I believe has a lot of progress on this question about how you extend this result to the non-invertible case. And the last thing, I'll just say it in words. So there are a lot more maps in Cn+1 beyond isomorphisms. But if I have a morphism in Cn+1, the domain has an ON action +1. The range has an ON +1 action, but the morphism only has an ON action. And so there's a question, even if you've kind of nailed this down and you understand what you mean by reflection positive spin n+1 fixed points, you still have to say which kind of maps between them you need to look at. And so at this point, I think the math side needs a boundary condition, it needs advice from the physics side. So if there's supposed to be an emergent spin invariance here, does that put a restriction on the kind of domain walls that you allow between phases? Because mathematically, we don't really know we have many, many, many choices we could make for the kinds of domain walls we look at. And if I'm imagining a general sort of categorified Kitaev conjecture, I need to know what kind of domain walls and defects, what structures those have, to line that up with something in topology. I'm going to stop. I'm sorry I went overtime.